Hi everyone, welcome to this episode of Keipert Labs. We're going to talk about the pH of salt solutions. So we're going to start off by doing a brief little recap of the Arrhenius theory of acids and bases, and then we're going to go through some examples of basic salts and then acidic salts. And so we're going to use the examples of the acetate ion and the ammonium ion as test cases to demonstrate why some ionic compounds form basic solutions and some form acidic solutions, versus those that just form neutral solutions. Okay, so let's do this. All right. So we're going to just quickly recap the Arrhenius's definitions. The reason being that Arrhenius's theory actually helps to explain the pH of solutions a little bit better than the Lowry-Bronsted theory. Okay, so remember, an acid produces hydrogen ions, that is, existing as H3O plus in water, and an Arrhenius base produces hydroxide ions in water. Okay, so for something to be acidic under Arrhenius's theory, so we would be writing equations that show the production of H plus, or if we can be a little bit more specific, a little bit more accurate, we can show the formation of hydronium, and then something to be basic, it's going to be showing it producing hydroxide ions in water. Okay, so let's start by having a look at the basic salts to begin with. Okay, the reason being that there are more examples we would come across that are basic than those that are acidic. Okay, so it makes sense then to spend a little bit more time thinking about that. So the first example that we're going to go through is acetate, or ethanoate. Okay, so a salt involving the acetate ion is formed from, so we're thinking, remember that neutralization, we're thinking acid plus base gives a salt plus water. Okay, so that's the kind of the general sort of reaction that's involved here. So we might form an acetate salt by, say, taking acetic acid and reacting it with sodium hydroxide, so acid plus a base, forming a salt, sodium acetate, and water. Okay, so if I was to take out the spectator ion in this case, which is our sodium ion, so I might write it like this. So acetic acid plus hydroxide goes to form the acetate ion plus water. Okay, so this is typically how we would form a salt like this. Okay, where this is acting as an acid. Okay, and so that makes this its conjugate base, if we were thinking about it in terms of Lowry-Bronsted theory. Okay, so that kind of gives us the first clue as to how this is going to behave. Okay, now the reason that we can then know what it's going to do to behave is that we can then say, right, well, let's imagine that now we have that acetate ion in water. We know that acetate can interact with water on its own, can react with water, where this is acting as a base and water is acting as an acid. Okay, so where a proton from here is going to join onto here to reform a molecule of acetic acid, and wouldn't you know it, ding ding, we are forming the hydroxide ion. Okay, so we've formed hydroxide, therefore this has acted as a base. This is something that is basic, because when we put it in solution, it has produced hydroxide ions. Okay, let's now have another look. Let's look at a different example. Okay, let's look at the hydrogen carbonate or bicarbonate ion. Okay, so same sort of deal. So be involved in this kind of a reaction, but so we can say, right, we put the bicarbonate ion in water, and it can react with water as a base to form H2CO3 plus the hydroxide ion. Okay, just as before, the formation of that hydroxide ion makes it it's acting as a base. Okay, so the presence, when we put this salt in water, the fact that it then interacts with and reacts with water to form a hydroxide ion makes it basic. Okay, so now let's switch gears and now have a look at an acidic salt, or the acidic salts. We're only going to go through one example because there's really only one ion that's of interest here, which is the ammonium ion. Okay, so to show how an ammonium salt might form, so we might have, let's go with something a little bit different. We would say an acid, nitric acid, plus ammonia as a base. We're going to donate a proton from here to here, so we're going to end up with, gives us the nitrate ion plus the ammonium ion. Okay, in this sort of situation. Or perhaps if I wanted to be, again, a little bit more accurate, reflecting that I'd have hydronium in solution, acid plus a base is going to give me NH4 plus water. Okay? But then what I can recognize, just as I did before, if I can, so that's how these sort of ions would actually form in a reaction. But then let's say I took something which was an ammonium compound, and I placed it in water. Okay, so I take the ammonium ion, it's surrounded by water molecules. This has an extra proton that it can donate to the awaiting water molecule to make ammonia and H3O plus. Okay, which remember is what's making it acting, so it's therefore acting as an acid. Okay, because hydronium is formed. Now it didn't contain hydronium originally, but by this process, the interaction with water, hydronium is formed, and so therefore it is acidic. Now, the thing that we could then quite reasonably say is, all right, let's look at, say, something like the chloride ion. Okay, what's the chloride ion going to do? Okay, now we could just as easily say that the chloride ion is formed from that same type of acid-base reaction. So maybe we were talking about hydrochloric acid reacting with sodium hydroxide to form sodium chloride and plus water. Okay, and so then we could say, all right, well, let's just kind of imagine that we're talking about the same, take out the sodium ion, that we get this chloride plus water. Okay, now the reality is that, so we can say that, and that's true. It is accurate, but it's not helpful, because then let's just say, all right, let's imagine that we put the chloride ion in water, and and then we're saying, all right, that we're going to go back to do this, and then we're going to form hydroxide, and aha, it's basic. But the reality is that on a practical level, this does not happen. Okay. Now, part of the reason for that is that, remember that HCl is a strong acid. So that is, it has the tendency to dissociate or to remove all of these protons to form the chloride ion. Okay? And so that happens very easily, which means that to reverse that process, to encourage for that chloride ion to grab onto a proton more strongly than something else, like a water molecule, it doesn't do that. It doesn't have that kind of that pulling power to actually take it off. So this reaction doesn't happen. So while we can draw it on paper, it doesn't actually do it. So that is that ions that form from strong acids are not considered basic. So that is nitrate, chloride, or sulfate. Okay? None of these are considered to be basic. Okay? But ones that arise from weak acids, because weak acids exist in an equilibrium that we don't fully dissociate, then that makes sense that we can force that equilibrium to go backwards. Okay, so hopefully this clears up a few things. Thanks very much for watching. Stay tuned for next time.